Now, the motion of a conductor through a fixed magnetic field also causes induction. This kind of induction is called motional EMF. So we're going to consider this circuit and this image here. We've got two conducting rods on top. They're connected on this end by a resistor, and on this end there's a metal bar running across. So all of these pieces create a closed circuit. And this circuit lives inside a magnetic field shown here. Okay, so as this vertical rod here moves to the right, the area that is enclosed by this circuit increases. So our magnetic flux is equal to the magnetic field times area. So if the magnetic field stays the same, but the area increases, we increase our magnetic flux. So if we look at Faraday's law, ignore the sign on it for now, and consider one loop, then the EMF we induce is equal to the changing magnetic flux over time. We said magnetic field was stationary or constant. The area is changing, so that's a changing area over a changing time. Okay. Now the area we can write as the length of this rod times some distance that it's moving through horizontally. Okay, so we're going to write that as BL delta X over delta T, because L is stationary, X is changing. The horizontal distance there is changing. And remember that a change in position over a change in time, that's a velocity or speed. So we can write this motional EMF as the magnetic field times the length of some conductor times the speed at which that conductor moves. Now this is a special case where the magnetic field and the magnetic field and this length of my bar here and the speed are all perpendicular to each other. So in this situation, Lenz's law will give us the direction of the induced magnetic field and current, and our right-hand rules, we're going to use both of them, give us the direction of the current and the magnetic force on the bar, which we're going to practice with the problem here. So we have a sliding bar, this bar here, with a length of 0.5 meters, and it moves at 2 meters per second in a magnetic field. Here, this magnetic field is into the board of a magnitude of 0.25 Tesla. We're going to find the, let's just say, induced EMF and current in the moving rod, calculate the magnitude and direction of the magnetic force on this bar, and then calculate the magnitude and direction of the force we have to apply to move that bar at constant speed of 2 meters per second.
In this problem, we're going to use the motional EMF to find an induced EMF and an induced current. So we have a conductor here, a conductor here. These are connected by a wire over here with a resistor. And then these two parallel conductors are also connected by this conductor here. This is a bar that I can slide in either direction. And when I move this bar, that's going to induce a change in magnetic flux within the loop, and that's going to induce an EMF, and that's going to induce a current. So this sliding bar has a length of 0.5 meters, and it moves at 2 meters per second to the right. So somebody is grabbing it and is moving it to the right. Okay. And we've got a magnetic field inside the loop here, a magnetic field that has a strength of 0.25 Tesla, and the total resistance of my circuit is 0.5 ohms. So our first part of this problem is to find the induced voltage, or the induced EMF, in the moving rod, question mark. To solve this problem, we could go right to our equation for motional EMF, or I can show you how you can get that equation for motional EMF from Faraday's law of induction. So if we think about just think about the magnitude of the induced EMF. So we're not going to put the minus sign here in this equation on it. It's going to be equal to n, which is the number of turns of our loop. There's only one here, times the change in magnetic flux over the change in time. Okay. Now in this problem, the magnetic field here is not changing, but the area is. As I slide this conductor here back and forth, I'm changing the area enclosed by the loop. So our change in flux is equal to delta BA cosine theta. So anything in here could change to change the flux. B could change, A could change, or this angle theta can change, which is the angle between my magnetic field and perpendicular to the loop. So in this case, perpendicular to the loop and my magnetic field are aligned with each other. So theta is 0, cosine of 0 is 1. Okay, and then we've got delta t here. So in this problem, B is a constant. It is not changing, but A is changing. So we can pop B out of our delta symbol. So B times the change in area over the change in time will equal our induced EMF. But let's imagine that I'm moving this rod. As I move it, I'm going to move it some increment delta x. So remember, maybe from last semester, that V is equal to delta x over delta t. Okay, the speed at which I'm moving my bar here. So B delta A over delta t. So B times, okay, the change in the area enclosed by my loop is going to be the length of it times its width. So the length here is not changing, that's L. And then, but I do have, actually, I can remove this delta here because L is not changing. But we are changing the length here of the bottom part of my loop. So we can replace that as delta x. So this is our length times width, okay? And then we're dividing it by the change in time. All right, so my area, at least the width of my area, is changing. That's the increment that is changing along the width, okay? So delta x. So we've got B, L delta x over delta t. So remember that delta x over delta t is V. So my motional EMF, the magnitude of it, is equal to B L V. The magnetic field, that's not changing, times the length of my conductor moving through the field times the speed at which I'm moving that conductor inside the field. That's my motional EMF. So that's going to equal, my magnetic field strength was 0.25 Tesla times the length of my rod here, which was 0.5 meters, times the speed at which I'm moving it, which is 2 meters per second. So my motional EMF, or my induced EMF here, has a magnitude of 0.25 volts, okay? So there we go. Now we can go ahead and think about the induced current. So if V is equal to IR from Ohm's law, then I, my induced current here, will equal to V, it's my induced EMF, over R, my resistance. So my induced current is 0.25 volts divided by the resistance of my circuit, 0.5 ohms. So my induced current is 0.5 amperes. Which direction is my current going to be within this circuit? Because my change in flux is increasing, B is staying the same, but my area is getting bigger as I'm moving my rod to the right here. Delta phi, my change in flux, is increasing. So let's remind us that delta phi is increasing in this problem. So a magnetic field will be induced due to a current in this loop here that will want to oppose this change in flux. So if the flux is going up, my magnetic field is into the board. Okay? Nature abhors a change in flux. It doesn't want this flux to change, so it's going to want to try to counteract this increase in flux by inducing a magnetic field that's going to be pointing in the opposite direction inside the loop as the magnetic field. So the permanent magnetic field is into the board here. So my induced magnetic field is going to be pointing out of the board inside the loop. So my induced magnetic field, this is my induced magnetic field inside the loop here, is going to be pointing out of the board toward me. Okay? So if it's pointing out of the board toward me, my induced magnetic field, I got my fingers here, second right-hand rule, my fingers are going to curl around the direction of the magnetic field. It's going to go out of the board toward me above the loop. So that means that my thumb is going to be pointing off in this direction. So the induced current is going to be pointing in this direction. This is a counterclockwise current. So my induced current is going to be counterclockwise. So we're going to induce this current, which induces the magnetic field that's trying to oppose this increase in the changing flux. Okay, so that's part A. Well, part A is really finding the motional EMF here, but we went ahead and found the current. So, and the direction that that current, induced current, is flowing inside the loop. So our next part is to calculate the magnitude and direction of the magnetic force on the bar. Okay, so the magnetic force, the magnitude of it acting on the bar will be I, L, B, sine theta. This angle theta is the angle between the current and the magnetic field. This is the magnetic force on the bar itself, okay? So the bar has a magnetic force with this induced current running through it, and it's subject to this permanent external magnetic field. So this magnetic field is our 0.25 Tesla. And our induced current and our magnetic field are perpendicular to each other, so that's sine of 90 degrees, so this is 1. So the magnitude of my force, magnetic force on the bar, will equal our induced current, which was 0.5 amperes, times the length of my conductor, which was 0.5 meters, times the strength of this permanent magnetic field, 0.25 Tesla. And so that gives me a magnetic force on the bar of 6.25 times 10 to the minus 2 newtons. Now, which direction is this magnetic force on the bar pointing? Well, we've already figured out that my current here through my conductor is going to be pointing up here. The current is running counterclockwise, so here my current is pointing up. All right, so my first right-hand rule will tell me the direction of the magnetic force on the bar. My fingers point in the direction of the magnetic field. So the magnetic field here in the loop, this is the permanent magnetic field, is pointing into the page, okay? My thumb is going to point in the direction of our charge carrier, which is the electron, so it's opposite the direction of the conventional current. My thumb's pointing down then. Since the electrons are the charge carrier, it's going to be the back of my hand that's going to tell me the direction of the magnetic force. And so the direction of the magnetic force is pointing in to the center of the loop here. So the direction of the magnetic force on this loop is pointing inward toward the center of the loop. Or you could say that it's pointing left, so we'll say it's to the left. All right, so that's my magnetic force. We got to have the direction, and we have the magnitude. All right, so then for part C, we want to calculate the applied force. So the applied force required to create this induced current and this induced EMF. This applied force required so that we get this steady speed of 2 meters per second to the right when we're pulling on this bar. Okay, so that's me taking my hand, the force that I have to apply to move it. That's what we're solving for. Now, we can use our idea of work from last semester in order to figure this out. So the applied work that I have to do with my hand, work is a force over a distance, so that will be my applied force through some distance. And the work is also the same as the power over time. Okay, it's the power through some time period. Then my applied force, I could solve this equation for applied force. Applied force is equal to the power times time over the distance that I have to pull. This distance that I have to pull in this direction, earlier we said v is equal to delta x over delta t, so that tells us that our distance, we could solve this for distance, distance is equal to a speed times the change in time, all right? So this distance that I'm pulling on that rod to move it to the right, that distance we could also write as v times delta t. So x is equal to v times t. So these delta t's cancel here. So the applied force they have to apply to move this rod at 2 meters per second is going to be the power over the speed. So our speed was our 2 meters per second. Now this power we can equate to the power of the circuit. So the power of our circuit is our induced current times our induced EMF. So our induced current was 0.5 amperes. Our induced EMF was 0.25 volts. Okay, and then we divide it by, let's move these towels out of the way, 2 meters per second. So 0.5 times 0.25 divided by 2 gives me my applied force. And this applied force is going to equal, oh, I've run out of room. But that's okay because this applied force also equals 6.25 times 10 to the minus 2 newtons. Okay. Our applied force on the bar equals the magnetic force acting on this bar. Okay, we have no acceleration of this bar. It is moving at a constant speed of 2 meters per second. So if I think about all the forces acting on this bar, I have my applied force in this direction, and I've got my magnetic force in this direction. So let's say this is my direction of my applied force here. And in order to move that rod at a constant speed, no acceleration, that means that my applied force has to equal the magnetic force that's opposing it.